Okay, good morning, everybody. So it's a great honor for me to start this meeting. So I should say it's my first Cool Star meeting. So I'm not that young, but it's my first Cool Star. So I hope you will enjoy my talk as much as I will enjoy the conference today. Okay, so I will speak about the earliest stage of low mass star formation and focus on the formation of disk, outflow, and protostar. So before I begin, I would like to thank all my collaborators that helped me to put all this work together over the past 15 years. So some of them are young PhD students and young postdocs. You might get to know them in the future. Okay, so here are the outline of my talk. So it's a big screen. Okay, so first I will introduce the big problems that we have to face when we deal with protostellar collapse. Then I will switch to actually dense core collapse, so introduce non-ideal MHD. And I will first speak about scale larger than 1 AU and speak about this formation at that scale. And then I will switch to sub-AU scale and speak about the protostar formation and the disk formation at this sub-AU scale. Through the talk, I will try to give you a flavor of the remaining open question and also about the perspective of where the field should go in the next years. So before I start, I should advertise this review that we put together last year at PP7. It has been presented there in Kyoto. Today, I will mainly focus on the numerical and theoretical side. So if you want to know more about observations of the scale and object I will present today, please go and see this review. Okay? Okay, so what are the fundamental issues? So I think you are all aware of it, angular momentum. So if we assume that angular momentum is conserved, and we look at the evolution of the ratio between the rotational energy and the gravitational energy, what we see is that as the radius decreases, this ratio increases, meaning that at some point, collapse will stop and we will form a disk. Okay? Yet, if we look at the specific angular momentum as a function of the radius, as compiled by Arnaud Beloche in 2013, we see that this angular momentum decreases. So first here at scale larger than the dense core, so this decrease is maybe due to turbulence in the ISM, but then you see that angular momentum is more or less conserved in the envelope and then decreases again at scale less than 100 AU. Meaning that in order to form a star, a collapsing core must get rid of most of this angular momentum. So problem number one. Problem number two, magnetic fields. So today, if we look at any scale in the galaxy down to the protostar, we find evidences of magnetic field. So from galactic plane, in molecular clouds, in class 0 protostar, and even in disks, we find evidences of this magnetic field. So we need to account for it and look at its evolution through the collapse down to the protostar. Now, if we do the same exercise and we look at the evolution of the magnetic energy as a function of the gravitational energy in the collapsing core, what you see is that this ratio doesn't depend on the radius, meaning that if magnetic field is strong at the beginning, it will stay strong at all scales. So we constrain in models the strength of magnetic field given this mu parameter, which is the mass-to-flux ratio, our critical mass-to-flux ratio. So if mu is larger than 1, magnetic field doesn't support the cloud, and the cloud can collapse. Observations tend to show that we have a relatively strong magnetic field for low-mass dense cores, so with mu between 2 and 5. Okay. Now, let's assume that magnetic flux is conserved. And we take typical value of magnetic field in the ISM, a few microgauss, and we compute what will be the magnetic field in a star. We end up with a magnetic field of 10 to the 10 Gauss. This is not what is observed. We observe a much weaker magnetic field. So as for angular momentum, a collapsing core must get rid of most of its magnetic flux. So this is the second problem we have to face. So I will try to show you how we can solve these problems today with our current capabilities. Okay. So now I would like to focus on the scale I will speak about today. So I think you all know this star formation evolutionary sequence based on the shape of the spectral energy distribution. And today I will focus on the transition between the prestellar phase and the protostellar phase. So this is the collapse phase. And so this collapse can be divided into 4 steps. So this classification has been done after the seminal work of Larson in '69, and it is still valid today for low mass stars. So let me go through these steps. So you see here the evolution of the temperature as a function of the density in a collapsing core. So you see that first we have an isothermal evolution. So this is what we call the first collapse. So because the dust can radiate freely the gravitational energy. So this first collapse proceeds up to density of 10 to the minus 13 grams per cc, where dust become opaque to its own radiation, and the gas and the dust are thermally coupled at this density. So the gas begin to heat, okay, and we stop the collapse. So we form what we call the first Larsen core, which is the first hydrostatic object that is formed. It has a size of about 5 to 10 AU. This first Larsen core will accrete material, so its temperature will increase until it will reach temperature of 2000 K at its center. And at 2000 K, H2 dissociation starts. And H2 dissociation is an endothermal reaction. So it will take energy to break H2 molecule. And we will recover a quasi-isothermal behavior, which will enable a second collapse to proceed down to stellar density, where we form what we call the second Larsen core, which is in fact the protostar. So I should insist here on the scale, and so first on the scale, so we go from AU down to stellar radius. Then you see the density will increase by 20 orders of magnitude. The temperature will increase by more than 4 orders of magnitude. We have different regime for the radiative transfer, so clearly it's a multi-physics and multi-scale problem we have to face here. Also, but the time scale, you see that most of the time is spent during the first collapse. This is the free fall time. But then, once the first Larsen core has been formed, the second collapse proceeds very quickly because the density are so high that the free fall time is small. Okay, so this is a textbook picture of forming a low mass protostar. So different components are forming. So we have here the first core. This first core drives a low velocity wide angle outflow, velocity of 1 kilometers per second. And then if we go deeper inside the first core, you find the protostar surrounded by a disk. And this system drives a powerful, highly collimated jet of velocity of 100 kilometers per second. So now the question is, what about the magnetic field evolution through all these components? We want also to know, when does the disk form? Does it form around the second core or around the first core? Do we have two disks? Does this disk fragment? And also, we want to know what are the initial conditions in the newborn protostar in terms of angular momentum and magnetic field. And of course, all of this will have some implication for further planet formation. Okay. Okay, so before I go to new results, I want to remind you what was the state of the art in 2010 when we were introducing ideal MHD in 3D dense core collapse simulation. So this was at the end of my PhD. So you see here a result of one solar mass dense core collapse with a moderate magnetic field. You see density map, view from the top, view from the edge. So you see that we form a structure here which looks like a disk, but it's not a disk, it's a pseudo disk. It's not rotationally supported. So when I speak about a disk, it is rotationally supported. So this pseudo disk is in fact infalling. You see here that we drive the low velocity outflow. So the maximum resolution here is 1 AU. Okay, but you see that so here we do not form any disk. So this is because magnetic braking is operating quite efficiently. Magnetic field is amplified in the central region, and because of the strong magnetic tension, magnetic field lines resist to the rotation of the cloud, and then angular momentum is transferred from the inner part to the envelope. And this is very efficient. So efficient that no disk was forming, and this has been called the magnetic braking catastrophe. So we were not forming disk. It's a problem because we know that this should form at some point. But at the same time, so it solves the angular momentum problem because there is no more angular momentum left in our system. Also, if we consider that this is ideal MHD, so magnetic field is frozen, meaning that magnetic field is amplified down to the smaller scale, meaning that we have not solved the magnetic flux problem in this kind of simulation. So in the past 15 years, a lot of work has been done in order to bring back the disk, this kind of model. So a few scenarios have been proposed, so I will quickly review them. So the first one is the late formation when there is no more envelope to accept the angular momentum from the central part, so the disk can form later on. There is also when the magnetic field and angular momentum are not initially aligned, okay, as it is observed, then magnetic braking weakens. There is also a turbulent reconnection that can operate, but it is mostly efficient in supersonic flows. And we know that for low mass cores, the turbulence is transonic or subsonic. And for me, the most promising one and most robust one is non-ideal MHD. Okay. So what is non-ideal MHD? So you have here the induction equation accounting for the three non-ideal terms. So you see in black the ideal MHD induction equation that I think you know. So, but here is the velocity of the neutral. So in order to get the velocity of the charges, we need to correct it. So then we see that the three terms appear. So first, the ohmic diffusion, the drift of electrons onto neutral, the ambipolar diffusion, the drift of ions onto neutral, and the Hall effect, which is the drift between positively and negatively charged particles. So this effect have a different effect on the behavior of the magnetic field. So you see that the Hall effect and the ambipolar diffusion can be written as a V cross B term, meaning that they will advect or rearrange the magnetic field line at a different velocity than the neutral one. And ohmic diffusion will provide some reconnection and magnetic flux diffusion. So now all the game is to know what are the strengths of these non-ideal effects. So we need to compute this resistivity, these eta parameters. And for that, we need to know the ionization state of the collapsing core. And we need to know then the gas grain chemistry, because grains can be the main charge carriers in this type of system. We also need to know what is the dust grain size distribution. So in what I will present today, we assume that it is fixed and it will not evolve with time. Okay. So here is an example of resistivity computed by Pierre Marchand back in 2016. So you see resistivity as a function of the density. Temperature also increases. You see that first ambipolar diffusion dominates, then the Hall effect, then again ambipolar diffusion, and then ohmic diffusion. Meaning that if we want to account for non-ideal imaging, we need to account for these three effects. It's even more important when you look at the characteristics timescale of this effect, and you compare it with the free-fall time, and you see that these timescales are much shorter than the free-fall time for a wide range of density, meaning that they will regulate the evolution of the magnetic field and its coupling with the gas for all these scales. Okay. So now what's happened when we introduce non-ideal MHD in the same model as I presented you before. So here, scale larger than 1 AU. You see here the magnetic field as a function of the density. In red, you have ideal MHD, so magnetic field is amplified with the density as expected. But with non-ideal MHD that you see here in blue, you see that there is a plateau here at 0.1 Gauss. This is because at high density, ambipolar diffusion starts to dominate and prevent any further magnetic field amplification at the center of the collapsing core. So the magnetic field is then much weaker in the central part, which weakens the magnetic braking efficiency, and then disk can form. So I show here two examples of disks that are forming. You see here maps of the plasma beta. So plasma beta is the ratio between the thermal pressure and the magnetic pressure. And you see that these disks are well described by plasma beta above unity, meaning that these disks are dominated by the thermal pressure. So they are kind of hydro disks. So it's in contrast with the ideal imaging case where we have a stronger magnetic field and much lower plasma beta. If you look at the magnetic field line orientation in the disk, you find that we have essentially a vertical magnetic field in these disks, meaning that so today we are now able to provide initial conditions for our colleagues doing protoplanetary disk studies in terms of magnetic field orientation and plasma beta. Okay. And so this result is quite robust about disk formation and the 0.1 Gauss plateau. So here I show you with different initial conditions, with initial turbulence or misalignment, 0.1 Gauss. This is done with IMAR code Ramses, so adaptive mesh refinement. If you do it with a particle code, SPH, you still have the plateau, 0.1 Gauss. Then if you introduce only, so you treat each of the non-ideal imaging term independently, so only ohmic diffusion or only Hall effect, you see that we form a disk, and the disk has the same properties as the one I've shown just before with ambipolar diffusion. So these results are quite robust and do not depend on initial condition or on the numerical technique. So first takeaway message. So you have seen that at scale larger than 1 AU, disk formation is regulated by non-ideal MHD processes. This magnetic regulation works for low and also high mass star. I did not show this today. And it's also quite robust in terms of time. You see here an evolution over more than 40,000 years, and you see that the disk doesn't change that much. Okay. So we have no prediction of magnetic field at AU scale. And I should say that this 0.1 Gauss is also consistent with paleomagnetic measurements in meteorites done in the solar system. So it's maybe a cosmic transparency, but this 0.1 Gauss seems to be consistent with that measurements. Okay. Okay, so now what about sub-AU? What happens if we go deeper in the collapsing core and go to the second collapse and second last core formation? So first, I show you here a hydro model without any rotation, so spherical collapse. So this is a simulation done by Asmita Bandare and her collaborator. So you see here Mach number, density, entropy, and temperature maps. So you see the first collapse that is proceeding. So, and then the first core that is forming. This first core will increase its temperature at the center, and it will trigger the second collapse right now. And you see the second collapse is very fast. Okay, it's almost instantaneous. So you see the second core that is forming. The second core is expanding, growing in size. It's because the Kelvin-Amos timescale is much longer than the accretion timescale, so it has no time to radiate the accreted energy. And you see the developments of this turbulent motion within the second core, even here in this spherical case. Okay. So we think that this turbulent motion are triggered, so sustained by the continuous accretion onto the second core. So this has been done so using the Pluto code, so 3D spherical geometry. But recently, so Annan Ali Ahmad, so PhD student in Saclay, performed the same with the Ramses code, so adaptive mesh refinement code in full 3D, and he found the same. So we have the turbulent motion that are developing inside the forming second core, and the second core is expanding. So the origin of this turbulent motion is not yet certain. So there are a few candidates, like the standing accretion shock instability. Or if you take the profile of this core and you apply some topological tools, you find that these profiles are unstable against the compressible buoyancy instability. So I invite you to read this paper by Leclerc et al., where they provide this kind of measurements. So now, the question is, what will be the impact of this turbulence, or maybe convection, on the foci magnetic field that will be imprinted into the forming protostar? So for that, we need to account for magnetic field and also for rotation. So first, rotation. So here, what I show is a movie of the forming protostar and its disk. So it's a simulation performed by Annan Ali Ahmad, so has been published early this year. So you see here in blue the disk, in green the protostar. You see here the streamlines of the material that is accreted onto the protostar. So you see it's mainly polar accretion. And you see here maps of the radiative flux. And you see the time here in years. Okay. So you see the second core that is forming, the disk that is forming concomitantly with the second core. Okay, and this disk expands to 1 AU size very rapidly. So in 1 year, we have reached the 1 AU size. So these processes are happening quite fast. So now I would like to focus on the radiative flux. So what we want to know is what is the radiative budget at the accretion shock. Okay. So here I show the efficiency of the accretion shock, so the ratio between the radiative flux and the accretion flux, so the incident kinetic energy, measured here in the equator, so here equatorial plane, so here at the disk, and also at the pole, so directly onto the protostar. So you see that at the equator, we have a low FAC, so 10 to the minus 3, meaning that we have a hot accretion, so the energy is not radiated away. But if you consider accretion onto the pole, you see that we have FAC close to 1, meaning that we have a supercritical shock. Most of the energy is radiated away. So if you think about cold versus hot accretion, you see that because of the anisotropy of the system, we can have both at the same time, okay, very early on. Also, I should say that at this point, the system of the star and the disk is a continuous system. So we do not have a clear boundary between the protostar and the disk, okay? So meaning that it's hard to apply the same tool as what will be performed later on at the class 1 stage, where you have a quite defined protostar and star disk interaction. Okay, so now what about magnetic field? So if we include magnetic field in this kind of simulation. So this has been done a few years ago, so by Neil Vete, who unfortunately quit academics today. So here we perform the same simulation, but with idle MHD in red and non-idle MHD accounting for ambipolar diffusion and ohmic diffusion. Okay. So here, I show the magnetic field as a function of the density. Ideal MHD, you see that, well, magnetic field is amplified down to the protostar. We end up with a very strong magnetic field of 10 to the 6 Gauss in the forming protostar. With non-ideal MHD, you see that, well, we are first amplifying magnetic field, then the plateau at 0.1 Gauss. This plateau is prolongated by the ohmic diffusion. And then when density gets higher, the medium gets fully ionized and the magnetic field recouples with the gas. Okay, but it starts with a much weaker magnetic field. So from the 0.1 Gauss, then magnetic field is amplified, but we end up with a magnetic field in the newborn protostar of about 1 kG, which is much more consistent with observation. So thanks to non-ideal MHD, you see that we have reduced the magnetic flux by more than 3 orders of magnitude in the forming protostar, which provides a solution to the magnetic flux problem. Now, if we look at the plasma beta, so you see that with ideal MHD in red, we have, again, a low plasma beta, strong magnetic field, so all the way down to the protostar. But with non-ideal MHD, you see that we have a high plasma beta, 10 to the 4, 10 to the 3, in the forming protostar, meaning that even if we are back to ideal MHD, we are back to ideal MHD, but in a weak field case, meaning that the magnetic field won't have a big impact on the gas dynamics at these scales. Okay? So I should say that also because of this first step where the magnetic field is strong at the AU scale, we still have an efficient magnetic braking. So most of the angular momentum is removed from the system. Okay. So now, on top of the thermal evolution, we can put the magnetic field evolution. So at a low density, the magnetic field is well coupled to the gas, and we are in the strong field regime. Okay. Then at intermediate density, the magnetic field decouples. So this is where non-ideal MHD operates. And then at much smaller scale, the magnetic field recouples with the gas evolution, but we are in the weak field case, so different ideal MHD regime. Now, if we look at the magnetic field morphology, so here I show magnetic field lines and isocontour of the density, ideal MHD at the top, non-ideal MHD at the bottom. You see that with ideal MHD, we have essentially toroidal magnetic field line, and this is because there is no more rotation. So magnetic field is like if there was no rotation. And with non-ideal MHD, you see that we form the second core, and we generate toroidal magnetic field surrounding this second core. So this is because here the differential rotation within the disk generates this toroidal component. So if we integrate this kind of model further in time, so this has been done by Kengo Tomida 10 years ago, so using only the ohmic diffusion in that case, and we see that after 1 month, this system is prone to drive the jet, highly collimated jet. And if you further integrate in time, so as done by Mashida and Basu, but with less physics, so they don't have lattice transfer in their models, so they could integrate further in time because it's less computationally expensive. And you see that we retrieve the textbook picture with the low velocity outflow driven at AU scale and the jet driven from the inner part. And this system is quite consistent with what is observed today in young protostars. What about the disk? So here I show density map and temperature map, ideal MHD, non-ideal MHD on the right. You see that with ideal MHD, no disk is forming. But with non-ideal MHD, we form a disk around the second core. This disk triggers spiral arm. It is gravitationally unstable. It expands quite rapidly, as in the hydro case, and it is in Keplerian rotation. I show this picture, and this picture is only 28 days after the second core formation. Okay, so it's very short time integration. This is because back in 2018, we had to stop the simulation because 1 second in the computer was 1 second in the real life, meaning that. So you can tell me if we have continued the simulation, we will have 6 years of evolution, but we are not. Okay, so here clearly we are at a bottleneck, so we need to increase the efficiency of our numerical tools, and for that we need to go to accelerated architecture like GPUs. So clearly in the next year, this is where the field will go. We need this long time integration. So this brings me to my conclusion. So as you have seen, non-ideal MHD cannot be ignored in a collapsing core model. It provides a solution at the earliest stage for the angular momentum and magnetic flux problem. We have seen that the second core disk quickly expands to AU size to merge with the first version core disk. Thanks to non-ideal MHD, we can imprint a foci magnetic field of 1 kilogauss in the newborn protostar. Okay. Now the open question is what happens to this foci field if turbulent motion develops later on, as it is the case with in hydro simulation. So we need to check the development of this instability in the MHD case. And this will, of course, test the robustness of our prediction for the magnetic properties in class 0 protostar. Perspective, clearly long-term integration at the sub-AU scale, so new tools are needed for us. And also, I did not speak about it, but it's a big deal, dust evolution. We think that dust should grow in forming protostar, and this has a huge impact on the MHD resistivity. So now, next generation of models should include the evolution of the dust grain size distribution in order to check the robustness of all what I've presented today. And I will stop here. Thank you.
Okay, so we have questions. I'll start over with Ofer. Yeah, Mike's going to come up.
So very nice review. Maybe I missed something, but why don't you get into toroidal field generation also in the ideal MHD?
Actually, at the second core scale, we do not find any toroidal field because there is no more rotation. Okay, so it's spherical collapse. But at the first core scale, we see some toroidal magnetic field. Okay, so different than the vertical magnetic field we see in the non-ideal MHD case. Okay.
Yeah, question over here.
Thank you.
Mission is based on, these simulations are often based on same particles as well. So are these simulations that you have shown here are based on same particles? If yes, then there is a concept of same collision radius. I'm just wondering how much is the effect on the disk formation coming from the value that you choose for the same collision radius?
Yes. So very good point. So almost all the simulations I presented are without sync particle. Only the one with the long-term integration are with sync particle. But you are right. So for second core sub-AU scale simulation, people don't use that much sync particle for the moment, okay, because we want to treat the radiative budget at the accretion shock. For the AU scale, so a lot of people use sync particles, and indeed, it's a big problem to know what are the sync particle parameters. So there are a few papers I can advise you. So by Patrick and Bell, by Mashida as well, where they look at the effect of the sync particle on the properties of the disk. And indeed, it can change a bit, but not that much on the size of the disk. It changes a lot the mass of the disks. Yeah.
Right, other questions? We got one over here. Can you repeat the question so that the Zoom people can hear it?
I'm Tom, space science.
Yeah, I can hear.
Okay. So both the first and the second core also have a disk, right? So the two disks will collide, and you have the mass pile up an extra or large planet formation taking place there? Okay, thank you. So the question is about the disk forming around the second core and the first core. Do they form independently, and will they merge eventually? And what it will, so what will be the interaction between the two disks? So it's ongoing work. So in the paper by Ahmad 2024, this one. So he has done a kind of parameter study, and he showed that depending on the lifetime of the first core, okay, the two disks can form independently or not. So in one case, if the first core has a short lifetime, then you form only the second core disk, and then this expand. But if the first core has a longer lifetime, then the two disks can
transform independently, and they eventually merge at the end of the simulation. But I cannot tell you how the interaction is done yet, so we need also a higher resolution at that scale to see. But clearly, we need to go through this in the coming years. Yes.
Time for one more quick question. If not, let's thank Benoît again. And let's see. The paper is going to be